Hi students, in this video I am going to introduce the concept of random variables. Most of the time when we consider a random experiment, we may not be interested in full physical description of the outcome. Rather, we may be interested in certain numerical characteristic of an outcome. Okay. For example, consider the situation of you appearing for GATE exam without any preparation. So it is going to be a random experiment as you cannot predict answer to any question with certainty. Okay. Here the sample space can be described like this. Okay. 65 tuple A1, A2, so on A65, where A is the option you have chosen for ith question. So A can be anything from A, B, C, D for I equal to 1 to 65. So the size of the sample space is going to be 4 to the power of 65. Okay, it's going to be this huge number. Fine. Thing is, you don't really care how you answer A or B or C or D for each individual question. What all you care is final score, which is a numerical summary of your performance. Most of the time, people are interested in this numerical aspect of an exam. Okay, if we quantify each way of attempting an exam by its score, then there are only few quantities to observe, which are possible scores 0, 1 to so on 100. Okay, if you only care about this final score of an exam, then there is no reason to deal with this huge space omega. Instead, we can look at the space of possible scores 0, 1 to so on 100, which looks much simpler than original sample space omega and easy to deal with, as this time outcomes are real numbers as opposed to some weird objects. And we should be happy to work with real numbers as we studied their properties and functions on real numbers with some analytical properties such as continuity, differentiation, integration. So we can use all calculus to understand the probability structure on R Borel sigma field. See, when we observe real quantities as outcomes, our event is going to be Borel set. So our event space is going to be the Borel sigma field. Okay. So whenever we are interested in some numerical aspect of the random experiment, the idea is to quantify each outcome with numerical summary. This leads to the concept of random variable. Before we look at the definition of the random variable, let's look at an example where we describe an event in terms of certain numerical characteristic. Okay. Here is an example. 3 balls are randomly selected without replacement from a box containing 20 balls numbered 1 through 20. If you bet that at least one of the drawn ball has a number greater than or equal to 17, what is the probability that we win the bet? Okay, here the sample space can be described like this. Here the outcomes are going to be 3 combination of these 20 numbers 1 to so on 20. Okay, so size of the sample space is going to be 20 choose 3. Fine. Let E be the event that we winning the bet. Now I am going to describe our event of interest E through some numerical aspect of the random experiment. Okay. First of all, I am going to quantify each outcome with certain numerical characteristic like this. Here X is a function from sample space to R. Each outcome here mapped to some number. Okay. Like this. This is how we are quantifying. Each selection we are quantifying with maximum of the selection. Here X can take the value 3, 4, 5, 6 or up to 20. Maximum of 3 combination will be at least 3 and at most 20. So X can take the value from 3 to 20. Let the script X denote the range of X, then the script X is going to be 3, 4, 5 so on up to 20. So this is going to be range of the X. Fine. Now let's describe our event of interest in terms of this X. Okay. Now E can be expressed in terms of X as follows. is going to consisting of all outcomes for which this numerical characteristic is greater than or equal to 17. See, at least one of the number in the selection is greater than or equal to 17 if and only if the maximum of the selection is greater than or equal to 17. Okay, that's why we can precisely describe E in terms of X like this. Okay, now, so first of all, let us see what is the probability of X take the value I. That is, what is the probability the maximum of the selection equal to I. If you want the maximum of the selection to be I, one of the number must be I, remaining two must be from 1 to I minus 1. So the probability of X equal to I is going to be, see, it's the probability of an outcome for which the maximum of the selection is I. So if you want maximum of the selection to be I, so we need to select that I in one choose one ways, and remaining two numbers must be coming from 1 to I minus 1. So that can be done in I minus 1 choose 2 ways. And the sample space size is 20 choose 3. Okay, here we can assume outcomes are equally likely as we are picking at random. Okay, so the probability of X equal to I is going to be I minus 1 choose 2 by 20 choose 3 for I equal to 3, 4, so on 20. Fine. Now, the probability of B winning the bet equal to what? Probability of this X greater than or equal to 17. Okay. Now, so X greater than or equal to 17 can be described union of 4 mutually exclusive events because X may be 17 or 18 or 19 or 20. Okay. In these cases, we are going to win the bet. So, this X greater than or equal to 17 we are writing as X equal to 17 union X equal to 18 union X equal to 19 union X equal to 20. Okay, so these are 4 mutually exclusive events. So by finite additivity, this probability we can write sum of these probabilities, probability of X equal to 17 plus probability of X equal to 18 plus probability of X equal to 19 plus probability of X equal to 20. And we know probability of X equal to I minus 1 choose 2 by 20 choose 3. So probability of X equal to 17 going to be 16 choose 2 by 20 choose 3. Probability of X equal to 18 going to be 17 choose 2 by 20 choose 3 and so on. These probabilities add up to 0.508. Okay, therefore the probability of we win the bet equal to 0.508. Okay, here X is an example of a random variable. Next we are going to see the definition of a random variable. Okay, definition. First of all, the job of the random variable is to quantify each outcome to a number. So it should be a function from sample space to real number. Okay, here is the technical definition for random variable. Let this triple omega script f be a probability space. A function x from omega to r is called random variable if inverse image of Borel sets under x should be events. That is, x inverse of b should be in script f for every b in script b, where the script b is the Borel sigma field. So this is the technical condition to be satisfied by function from omega to r. Okay, fine. Now in practice, we don't need to check this condition for all Borel sets. It's enough to check for this subcollection. Okay, script j consisting of all intervals of this form, infinite semi-closed intervals, minus infinity to x, where x belongs to r. Okay, and this fact stated in the next theorem. Okay, theorem. Let x be a random variable on the probability space omega script f p if and only if inverse image of all these infinite semi-closed intervals belongs to script f. Okay, so it's enough to check for this type of intervals. Okay, so I gave a detailed proof in the notes. Here I am going to give an outline. Okay, here there are two directions we need to show. First of all, one direction is take x is a random variable, then show that this condition must be true. See, when we know x is a random variable, we know that x inverse b belongs to script f for all b belongs to script b, right? In particular, if I take b equal to minus infinity to x, which is also going to be Borel set, right? Actually, we know that all these intervals are Borel set, so the script j is going to be subset of this script b. Okay, so in particular, if you pick intervals of this form as the Borel set, you must have this. Okay, so one direction is pretty straightforward. Okay, other direction. So if we know this, we need to show that x is a random variable. For that, we need to show that inverse image of Borel sets are in script f. Okay, so let's say suppose we have x inverse of minus infinity to x belongs to script f for all x. Then we need to show that inverse image of all Borel sets are in script f. Okay, for that what we do, let us consider script b naught consisting of all Borel sets for which this is true. Okay, so if you want x to be random variable, the script b naught should be equal to all script b because it should be true for all Borel sets, right? So obviously anyway, so far we know this is subset of the script b. Also we know that when you know this, we can see that this all script j is going to be contained in the script b naught. Okay, for all this kind of intervals, this is true. So all this type of intervals will be sitting in script b naught. That much we know. In the notes, what we did, first we show that this script b naught is sigma field. Once you showed that, then the sigma field generated by script j is going to be subset of script b naught because sigma field generated by script j means smallest sigma field which contains script j. So every other sigma field which contains script j should also contain sigma field generated by script j. That's fine. Okay, but we know that sigma field generated by the script j actually the Borel sigma field. Okay, so therefore what we have, the script b contained in script b naught, and we already know that script b naught is contained in script b. Therefore we can conclude that the script b naught equal to script b. Therefore that means this is true for all b. Therefore x inverse b belongs to script f for all b belongs to script b. That implies x is random variable. Okay, so this is the outline proof. I give a detailed proof in the notes. Okay, please try to understand. Okay, before we see an example of a random variable, let's try to understand this. The random variable x is a function from omega to r, right? Okay, so this is omega, this is r. Okay, for any subset of r, the inverse image is going to be some subset of omega. So when I say inverse image of minus infinity to x, which is going to be subset of omega. So how do you understand this? It consisting of all outcomes in omega for which the x of omega is sitting in interval minus infinity to x. Okay, so this is exactly we mean by inverse image of minus infinity to x. Okay, fine. Okay, example, let omega script f be a measurable space, that is omega is a sample space, script f is an event space, and E is a subset of omega. Then IE defined like this. I sub E, the function from omega to r. Okay, it's a two valid function. It takes only 0 or 1. Here IE quantifies each outcome to 0 or 1. Okay, so an outcome will be quantified to 1 if an outcome is in E, otherwise it will be quantified to 0. Okay, such a function is called indicator function of E. And this I is a random variable if and only if E is an event. That is, if E come from scriptf. Okay. Let's try to verify this. Let's look at inverse image of minus infinity to x. We know what it means. Consisting of all outcomes for which I of omega sitting in interval minus infinity to x. Okay. We know that I of omega always either 0 or 1, right? Okay. Now, if x less than 0, neither 0 nor 1 will be sitting in this range. That's why. So, no outcome can be in this inverse image. So, in that case, it should be empty. If x is between 0 and 1, including 0 but excluding 1, in that case, only 0 can go inside, right? So, in that case, outcomes which are quantified to 0 can come inside. So, the inverse image will consist of only outcomes which are quantified to 0. Those are precisely E complement. So, this is going to be E complement. If x greater than or equal to 1, in that case, both 0 and 1 both can come inside. So, in that case, for every outcome will be quantified inside this range. So, that's why this inverse image will consisting of all outcomes. That's why in that case it's going to be all sample space. Okay. So now we know that in any sigma field, this empty set and all space always will be there. The only question about this E complement. That's why I is random variable if and only if this E complement is an event. That means E complement is in scriptf. That is if and only if E belongs to scriptf, because sigma field is closed under complementation. If E complement is there, E should be there. If E is there, E complement should be there. Okay, that's why this I is a random variable if and only if E is a event. Okay. Okay, next example. In a random experiment of tossing a coin, we know that sample space will consist of just two possible outcomes, head, tail. Okay, this is sample space, and our event space we are taking as all parts of omega. Then x is defined like this: the function from omega to r, and head map to 1, tail map to 0. Okay, so this is nothing but x you can recognize as indicator function of singleton h. Okay, because if you take E equal to singleton h, then E complement going to be singleton t. So just like we write earlier, when x less than 0, inverse image of this is going to be empty. When x between 0 and 1, this should be E complement. Okay, and this is all omega. Okay, obviously this x is going to be random variable. Fine. Next. Okay, next example. Let's consider a random experiment of tossing a coin twice. Okay, then there are four possible outcomes as we know: head, 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 tail, tail, head, tail, tail. Okay, here we take event space to be all parts set of omega. Now, here we are quantifying each outcome with number of heads. Okay, here x is a function from omega to r. Each outcome we are quantifying with number of heads in outcome. Okay, so x can take the value 0, 1, 2. This is the range of this function. Okay, that means here head will be quantified to 2, head tail will be quantified to 1, this also 1, this is going to be 0, right? So now to verify if it is a random variable, we look at inverse image of interval minus infinity to x. We know what it means: all outcomes in sample space for which the number of heads sitting in the interval minus infinity to x. Okay, if x less than 0, no outcome will be quantified inside here. So That's why inverse image is going to be empty. If x between 0 and 1, including 0, excluding 1, only singleton tail will be quantified within this interval. So that's why the inverse image is going to be singleton tail. When x between 1 and 2, including 1, excluding 2, all these three will be quantified in this interval. So in that case, inverse image is going to be this one. Now when x greater than or equal to, okay, all 0, 1, 2, everything will be quantified inside. So all outcomes will be included in the inverse image. So that's why inverse image is all omega. Anyway, our event space is part set of omega. Everything is subset of omega. So all R belongs to script f. So this is a random variable. Okay, fine. Note here, people proved that when the sample space is uncountable, like an interval, then it is not possible to come up with any probability measure satisfying three axioms on this space. That means we cannot include every subset of omega in our event space to assign probabilities. Okay, so we may have to exclude some bad subsets, something called non-measurable sets. Okay, so in general, our event space may not be all part set of omega. But when the sample space is finite or countable infinite, then one can include every subset of omega in our event space to assign probabilities. So still we can come up with probability measure satisfying three axioms by keeping event space all part set of omega. Okay. In a probability space, if you take script f to be power set of omega, if that is possible, then any function from omega to r will be a random variable. Because whenever you look at inverse image of any Borel set, that is going to be subset of omega, and every subset of omega including power set of omega. So which is our script f now. So in this case, we don't even have to check this condition. So obviously whatever function we take, this condition will be fine. Okay. Thing is, when sample space is uncountable, it's possible to construct a function from sample space to R which is not a random variable. But good news is they don't come in practice. Okay, whatever functions that are associated with a numerical characteristics that occur in practice, they are all good. In practice, from now on, we never have to check this condition. Whatever may be the sample space, finite or uncountable or countable infinite. In all cases, we take every function that we can think of as a random variable. Okay, now let's look at some examples of random variables associated with random experiment. Experiment 1. Rolling a pair of dice. Here x is sum of dice. Then x can take the value 2, 3, 4, so on 12. Okay, this is the range of x. Experiment 2. Tossing a coin until head appears. Here x is number of trials required. We may require any number of trials to see head. So here the range of x is 1, 2, 3 and so on, natural numbers. In experiment 3, selecting a random student in a class. Here x is weight of the student in kgs. Here x can take any value in the interval 40 to 70 kgs. Okay. In the experiment 1, the range of x is finite. In experiment 2, the range of x is countably infinite. In experiment 3, range of x is interval, which is uncountable set. Okay, fine. Next, probability distribution of a random variable. First of all, we have a probability structure on our original measurable space omega script f. That is, we have a probability function p from script f to r. Using random variable, we quantify each outcome with a real number. So that will give us a new target space R and the Borel sigma field as the event space. Okay. Once we have a random variable, each event of interest described using Borel sets. So we want to have a probability structure on this space. So we want to come up with a probability function Px from this Borel sigma field to R. Okay. So we should be able to assign the Px of B for all Borel sets. Question is, how do we do that? Our idea is to transport the probability structure that we have on this space to this space. Okay. The reason is any event of interest actually event in scriptf that can be described in terms of Borel set and random variable x. Okay, so there must be a connection between this Borel set and event here. Since x is a random variable, we know that inverse image of Borel set is sitting in descriptors. So inverse image of a Borel set is event. So we can assign probability of this event using P, because P is the probability function on this space. Okay. So we are going to define the Px of B as the probability of x inverse B. This is how we transport the probability structure on this space to this space. Okay. Now we are going to verify that this Px satisfies three axioms of probability. So the Px will be valid probability measure on this space. Okay. That will give us a new probability space R script B Px. This is called induced probability space by x on omega script f P. And this Px is called probability distribution of random variable x. Okay. Now we are going to see these things. Let x be a random variable defined on probability space omega script of P. We define the Px is a function from Borel sigma field to R, defined like this. Px of B as probability of x inverse B, where x inverse B will be event in the script f, that consisting of all outcomes in omega for which x omega sitting in this Borel set B. That is the meaning of x inverse B. Okay, this is our definition of the Px. Now we are going to verify that this Px satisfies three axioms of probability. Okay, so claim this Px is a probability measure on this space R script B. We are going to verify three axioms. Axiom 1. First of all, the Px of B according to definition, which is the probability of x inverse B. X inverse B some event in script f. We know that from axiom 1 of the probability P, the probability of any event must be non-negative. So we can be sure that this is non-negative. Therefore, axiom 1 is verified. Fine. Next, let's verify axiom 2. Next, Px of R. Okay. So we want to show that Px of the whole space R must be 1. Okay. And according to definition, the Px of R going to be probability of x inverse R. Okay. Now, inverse image of all R going to be all domain, which is omega. X is a function from omega to R, right? Okay. Inverse image of all codomain going to all domain, which is omega, and we know that the probability of omega is 1 using axiom 2 for P. Okay, so therefore the Px of R going to be 1. So axiom 2 also verified. Okay, fine. Now let's verify axiom 3. Let B1, B2, so on, Bn are countable collection of mutually exclusive event in script B. Then we need to show that Px of union I equal to 1 to infinity, Bi equal to summation I equal to 1 to infinity Px of Bi to verify axiom 3. Okay. So let's start with the left hand side. The Px of union I equal to 1 to infinity Bi equal to, according to definition of Px, it should be probability of x inverse of union I equal to 1 to infinity Bi. Okay. X inverse of union I equal to 1 to infinity Bi, we can write union of x inverse Bi. So in the next step, we write this part as union I equal to 1 to infinity x inverse Bi. Now Since we know B1, B2, so on, Bn are mutually exclusive event, then we can say their inverse images are also going to be mutually exclusive events in scripters. Okay. The reason is this. For example, let's say this is omega, this is R. Let's say we have two events here. Let's say Bi, some Bj. Both are mutually exclusive, no overlapping. For suppose if you think that their inverse images are overlapping, let's say like this. Okay, this is the inverse image of X inverse Bi. Let's say inverse images of X inverse Bj like this. So let's say they overlap. Okay, this is some common outcome to both inverse images. Then what happened in this case? This outcome going into Bi as well as Bj. That means these two must be different numbers, right? One outcome mapping to two different numbers. That means x is not even a function, but random variable is a function. So we cannot have this overlapping. Okay, so this cannot happen. Okay, that's why when B1, B2, so on, Bn are mutually exclusive, then their inverse images also must be mutually exclusive in scripters. So therefore, so all these events going to be again mutually exclusive. Now we can apply countable additivity axiom 3 for P. So this is going to be summation I equal to 1 to infinity probability of X inverse Bi, because axiom 3 for P. As we know, these are mutually exclusive. We can apply axiom 3 for P. Okay. So again, so the probability of X inverse Bi going to be what? By definition, which is Px of Bi. So next step I will write that. So each term going to be what? Px of Bi. Summation I equal to 1 to infinity Px of Bi. So we have, so therefore we have the Px of union I equal to 1 to infinity Bi equal to summation I equal to 1 to infinity Px of Bi. So axiom 3 is verified. Okay. So therefore, Px is a probability measure on this measurable space or script B. Hence, we have a new probability space or script B Px. This is the probability space. This is called induced probability space by random variable x on this probability space omega script of P. Okay, and this Px is called probability distribution of random variable x. This probability function Px is called probability distribution of random variable x. Okay. Okay. Let me introduce a notation here. The script x is a notation for range of x. That is, the script x will consist of the possible values x can take. Okay. Theorem: Px of B equal to Px of B intersection script x for all B belongs to script B. Let's prove this. We can see that for any B belongs to script B, we can write B equal to B intersection R, since B is subset of real numbers, right? Now, the Px of B we can write Px of B intersection R. Now this R we can replace with script x union script x complement. If we apply distributive laws inside, Px of B intersection script x union B intersection script x complement. Okay. Next, by the definition of the Px, we can write P of x inverse of this B intersection script x union B intersection script x complement. Okay. Now we know that inverse image of the union is going to be union of the inverse images. So next step we can write P of x inverse of B intersection script x union x inverse of B intersection script x complement. Now we can see that this is going to be empty because B intersection script x complement is part of the outside range of x. Okay, no outcome is going to outside range of x. So that's why inverse image of any part of the outside range will be empty. So this is going to be empty. So in the next step we can write the probability of x inverse of b intersection script x. This part we are replacing with empty. So that's why we can write the probability of x inverse of b intersection script x. Okay, this is nothing but px of b intersection script x. Okay, so therefore we have the px of b equal to px of b intersection script x for all b belongs to script b. Fine. In our course, the script x, that is the range of random variable x, generally be finite or countable infinite or interval of real numbers. When the range of x is finite or countable infinite, then x is called discrete random variable. Okay. When the range of x is interval of real numbers, then x is called continuous random variable. Okay. Fine. Let x be a discrete random variable on the probability space omega script of p, that is the script x. The range of the random variable x is either finite or countable infinite. That's what we mean by discrete random variable. Then for any b belongs to script b, the b intersection script x also going to be finite or countable infinite, because b intersection script x again subset of script x. Okay. From previous theorem we know that the px of b is same as px of b intersection script x. Okay. Now this b intersection script x we can write union of the singleton x, where x varying over b intersection script x. Because this b intersection script x either finite or countable infinite, this union going to be either finite union or countably infinite union. And singletons are always mutually exclusive, so we can apply either finite additivity or countable additivity. So we can write that summation x belongs to b intersection script x px of singleton x. Okay, the reason is we are applying either finite additivity or countable additivity according to whether b intersection script x is finite or countable infinite. Okay, so therefore we have px of b equal to summation x belongs to b intersection script x px of the singleton x for any b belongs to script b. This is how we can compute the probability of any Borel set under Px if you know the probabilities of the singletons under Px. Okay, so this is how we can compute. All we need to know is the probabilities of the singleton x for x belongs to script x. Okay, under Px. Example. Consider the random experiment of rolling a pair of fair dice. Here the sample space is going to be this. Here sample space consisting of order pair I comma j, where ij vary from 1 to 6. Okay, there will be 36 possible outcomes that are equally likely. Okay, let omega script of p be a probability space. Here omega is the sample space. Here the event space script f we are taking all or set of omega, and our probability function is going to be this. P of a we are computing as number of elements in a by number of elements in omega, which makes sense as we have a finite sample space with equally likely outcomes. Okay. Now let's look at random variable defined on this probability space, which denotes the sum of the dice. Okay, so x is a function from omega to r with a mapping I comma j outcome quantified to I plus j. Okay, the range of this function, the script x is going to be 2, 3, so on 12, which is a finite, so x is going to be discrete random variable. In this case, for any Borel set, the px of b computed as this summation of this px of the singleton x, where x varying over b intersection script x. Okay, from above result. Let's look at probabilities of few singletons under this px. Okay, px of singleton 2, which means probability of x inverse 2, which is the event in script f which consisting of all outcomes that are quantified to 2. That means all outcomes whose sum of the die is equal to 2. So only outcome 1 comma 1 add up to 2. So this is nothing but singleton 1 comma 2. The probability of this event is 1 by 36. Okay. Similarly, if you look at px of singleton 3, which means probability of x inverse 3, this x inverse 3 is a event in script f which consisting of all outcomes that are quantified to 3. That means sum of the die is equal to 3. So only this 1, 2 and 2, 1 add up to 3. So that means that event going to be consisting of these two outcomes. So the probability of this event going to be 2 by 36. Okay. Now, if you want to compute the probability of closed interval 1, 3 under this px, okay, so we know it's going to be sum of the probabilities of singleton x, where x varying over closed interval 1, 3 intersection with script x, which is going to be closed interval 1, 3 intersection script x is set consisting of 2 and 3. So the summation varying over 2 and 3. That's why we have a px of singleton 2 plus px of singleton 3. Okay. So px of closed interval 1, 3 going to be px of the singleton 2 plus px of the singleton 3. Okay. So we know these two probabilities. So let's plug it here. So 1 by 36 plus 2 by 36, it add up to 1 by 12. Okay, fine. Next, once we know probabilities of all the singletons, okay, for 2, 3, so on up to 12, then we can compute px of b for any Borel set. Okay, it's going to be px of the singleton x, where x varying over b intersection with script x. Okay, this script x is here 2, 3 up to 12. Okay, so once we know these values, okay, these 11 probabilities, then we can deal with the probability of any Borel set. Okay, fine. In the last example, we looked at the discrete random variable. Now let's look at a continuous random variable. Okay. Consider a random experiment of picking a real number from closed interval 0, 1. Then the sample space omega will be again closed interval 0, 1. This time outcomes are real numbers, right? So let's quantify them as it is. So our random variable x going to be function from omega to r with a mapping x map to x only. So the range of the random variable x going to be again closed interval 0, 1. So the script x equal to closed interval 0, 1. Now question is, what should be the probability distribution px? Okay, that is how to assign probabilities to these Borel sets. Okay, it is not easy as it is in the previous example, but for certain Borel sets we can assign these probabilities intuitively. Okay, if you consider Borel set of this form, open A closed B interval, which is a Borel set. Okay, so I can assign probability of this interval as length of interval, which is going to be b minus a. Let me convince you why it makes sense. Okay, the probability of we pick a number from interval ab should be proportional to the length of the interval, right? At least, and as we pick number at random, this probability should not depend on the location of the interval. It should depend only on length of the interval. Okay, so at least we feel that this probability should be like a k times b minus a, where k is a proportional constant, b minus a is the length of the interval. And we should know that the probability of interval 0, 1 should be equal to 1, because we pick a number from interval 0, 1. It is kind of a sure event, right? So, and according to this, it should be k times 1 minus 0, which is k. That is, this should be equal to 1. So, k must be equal to 1. So, this k must be 1. So, this makes sense. Okay. So, that's why for a Borel sets of this form, open A, closed B, for 0 less than or equal to A less than B less than or equal to 1, the px of interval AB taken as length of the interval, which is B minus A. Okay, fine. Now, it can be shown in more advanced course on probability theory that probability distribution Px will be completely determined on all Borel sigma field once we know this Px values on this type of intervals. The intuitive reason is the Borel sigma field generated by this type of intervals. That is, any Borel set can be expressed in terms of this type of intervals using union, complementation, intersection operations, right? So technically, we should be able to assign probability to any Borel set once we know the probability values on these intervals. Okay, fine. And we also know that the Borel sigma field also generated by this type of intervals minus infinity to closed x, where x belongs to R. So, knowing px values on this type of intervals will also uniquely determine probability distribution px on all Borel sigma fields. This defines an important function called cumulative distribution function of a random variable. Okay, we simply call it CDF. Here is the definition. Let x be a random variable defined on probability space omega script of t. Then the function capital F sub x, it's a function from real numbers to real number, defined like this. Function value at x defined as probability of interval minus infinity to closed x under px. Okay, we know what we mean by px of minus infinity to x, which means probability of event x inverse of minus infinity to x. Okay, x inverse of minus infinity to x is event in script f. Okay, so which means that event is consisting of all outcomes for which x omega sitting in minus infinity to x. Okay, this can also be written like this: all outcomes for which x omega less than or equal to x. Okay, so for this event, the simple notation is we write x less than or equal to x. Whenever we write like this, x less than or equal to x, we mean collection of all outcomes for which x omega less than or equal to x. That's why we can also write like this: probability of x less than or equal to x means we mean this px of minus infinity to closed x. Okay, so fine. So this is a cumulative distribution function we call CDF. Okay, a good thing about this CDF is which is a real variable function. Okay, the bad thing about the px is the probability distribution px is a set function whose domain is Borel sigma field. Okay, it's not easy to deal with set functions, but we can deal with real variable function because we can use all calculus to study and understand real variable function. Okay, and knowing CDF values at x means knowing the probabilities of these events minus infinity to closed x. Okay, so that means This knowing these CDF function values will uniquely determine probability distribution Px on all Borel sigma field. That's why it's enough to study the CDF function to study and understand the probability distribution of the random variable x. Okay, so from now on, our focus will be mainly on the CDF function. Okay, fine. So, okay, let me stop now. I'll continue in the next video. Okay, okay, thank you.